to celebrate with the experiments, I have here Tiziano Camporesi, spokesperson for the CMS experiments. Tiziano, we made it.
Yes,
the new
ciao,
era
Paola.
started. The new era started.
There was a moment of great excitement a few minutes ago here.
The Big Bang.
And now, 13.7 billion years later,
Here we are in the infinite vastness of the universe.
which contains our galaxy,
The Milky Way.
our solar system,
Earth.
We're now moving on to point one of the LHC with Alex Cerri. Ciao Alessandro.
Ciao,
Hi.
buongiorno. Good morning.
Good morning. So before we didn't speak a lot about Atlas. Atlas is the largest of the 4 LHC detectors. Can you tell us more about this fabulous experiment?
Indeed, it's an impressive, large experiment. If you have a chance of visiting, if you have had the chance of visiting it while we were in shutdown, it's 25 by 25 by 45 meters. It's the largest of the experiments. It's a huge cathedral of particle physics, basically, and it's one of the 2 general-purpose experiments at the LHC together with CMS, which basically means that we look at collisions, looking for several different phenomena, among which, as you know, the Higgs boson that we discovered.
Exactly, I was about to mention, we didn't mention yet, but we should say that this was an enormous discovery.
I happen to be on Atlas, but I'm trying to be
neutral here. It was an enormous
was
discovery, and did you expect it to find it at 7 TeB?
Well, we worked hard to find it, of course, you know. The nice thing about these kind of experiments is that you are really at the forefront, so you can never be sure what to expect. We had hints that possibly in certain models the Higgs boson could be there and could be already found at these energies. But,
and now one wonders, what's next? Why bothering going higher in energy? You have the Higgs, you have the standard model, it's complete. What's next?
It's complete, but we know it's flawed. And we know that there is something else to discover. The question is whether and how much we can discover with this next run. The discovery potential is going to be very, very large. We do expect that something could possibly be found in the near future. But no matter whether we find something or not, this is going to be an important piece of information in the puzzle of building a more complete model than the standard model itself.
That's what makes it so exciting to go to 13 TeV now. We are jumping by almost twice the order of magnitude in energy.
Yeah, I think Alex made important points there. That the Higgs boson now, as we discussed, is discovery is one thing. Now we have a tool, right, to explore with. I think that's something that certainly Atlas and CMS will be focusing on in the coming years.
Definitely, it's going to be important to refine and understand more about the properties of this new particle, and it's going to give us hints on what could possibly be beyond as well.
Because we have still some very big questions, as you alluded to. The standard model is wonderful. It's somewhat complete, but there's so many big questions out there. And one thing that has been brought up by many people are curious about is this thing that we refer to as dark matter. Is Atlas going to be able to look for dark matter?
Well, we know that dark matter is there from observing the cosmos. If we discover new particles, then some of these new particles may be responsible for accounting for this dark matter. So in this respect, we could be able to give at least a part of the answer to what dark matter is made of.
It's quite a special situation, though, that you before you had hints from a theory. The Higgs theory was extremely precise, and it was a good hint. You didn't tell which energy you would find the particle, but it had to be there. Everybody was convinced. Now you have cosmology telling you that there is something beyond the standard model, and that's dark matter. So it's quite a special situation that makes. Does it make you feel closer to astrophysics and cosmology?
Well, cosmology and particle physics are getting closer and closer as they become more and more scrupulous in understanding how the universe works. And yeah, it's definitely exciting. And it's something that we've seen growing in the last 10, 15 years. So definitely, yes, there is a lot of exchange at this point. And the LHC what's exciting is actually that it is the kind of machine that allows you to explore new physics in a very broad spectrum. Is what we call a discovery machine, rather than something that allows you to measure precisely properties of particles that you know are already there.
So, Alessandro, thank you very much for being with us. We'll come back to Atlas soon. We're going to leave LHCb now and move on to the ALICE experiment at point 2 of the LHC. Hello, Alice.
Hello, can you hear us?
Yes, we can hear you. I don't have your name. Can you say your name, please?
Hannes Wessels.
Hi, Hannes. And what is your role in the ALICE experiment?
I'm one of the deputies.
One of the deputy spokesperson, okay. So before, when we were talking to your spokesperson, we didn't dwell too much on the detector itself. We would like to know more about ALICE. We see in the banner behind you, it's called a Large Ion Collider Experiment. So you collide ions.
If the machine lets us, yes.
Yes,
so we are gearing up
will.
with the exactly. So our prime time will be in November, and we're gearing up with the proton beams now, and actually perform important reference measurements for our measurements to come in November.
So in a sense, this is Steve. In a sense, you use the proton collisions to set certain levels that you can understand or calibrate your detector?
Well, no, actually, it's really physics motivated. So what we want to do if we collide ions, we want to really study what happens if you have large lumps of quarks and gluons mashed. And these properties you can only understand if you understand what happens in elementary PP collisions. So everything that we study when we collide heavy ions, we compare to what is happening if we have a very small system. So we can study the transport properties, how it expands, how it behaves. And this is really the goal of our investigations.
Mm-hmm. And now, given the measurements that were made, you made some very important measurements during run 1. Are there specific goals that you have in mind for run 2?
Absolutely. So, I mean, with the increase in energy and the increase in luminosity, so we will have much more data. At the same time, you've heard that we've actually used the shutdown to consolidate the detector to be able to take twice as much rate. And through this, we will be able to be what we call much more differential in our observations, really study specifically the transport properties of the matter.
That sounds fascinating. You're really looking, well, many people describe this as looking at the very early universe. You're seeing the properties of quarks and gluons before formation of protons and neutrons.
Exactly. And how this actually expands into the vacuum.
Mm-hmm. Excellent.
Thank you, Hannes. I can see Rebecca Suarez-Gonzalez at the CMS control room. Rebecca, hello. Can you hear us? Rebecca, we see you, but I don't hear you.
Could be the same for her.
Yes, I think she doesn't hear us. Rebecca, hello?
Hello, can you hear me?
Yes. Okay, that's
Very good.
great. Hi, Rebecca. Welcome.
Hi. Thank
So
you.
while we're waiting for beams to be re-injected in the LHC, we thought it would be a good idea to discuss a bit about the detectors, the CMS detectors. It's
Okay.
what is special about CMS? Tell us how it works and.
Well, what is special about CMS is that it's compact. We have a very big solenoid magnet that is the largest solenoid magnet that has ever been built, that usually operates at 4 Tesla. And due to having this very big magnet, we can have a very strong magnetic field within the experiment, and that allows us to have most of the subdetectors inside the magnet. Like this, we can be a bit smaller than Atlas, for example, but what happens is that, on the other hand, we are much heavier.
So this is Steve here. I have some questions coming from across the ring. There's a whole lot of things that we all want to look for in the coming years. Do you have a favorite topic of physics that you think is something that could happen in the coming years with this higher energy?
So I do have favorite physics topics for the next rounds. In particular, I like new physics that involve top quarks and Higgs bosons. I think they're very interesting, the interplay between these two particles, because the top quark is the heaviest quark that we have found so far, and it has a very strong relationship with the Higgs and with stability of the universe. So there are a lot of models of new physics that involves top quarks or top partners that I think they are particularly interesting, because these kind of things give nice signatures experimental that are very fun to study, and they could be a window to many different theories beyond the standard model.
Well, yeah, I think that's a very important point. It's very interesting physics. Many people don't really understand that the Higgs boson, finding it was only our first step. And now exploring it, like you would like to do, looking at its interactions with the top quark, for example, measuring all of its properties, might be our way to find what's beyond this beautiful standard model we have.
Yes, I agree.
Yeah, I say beautiful, but
Yes.
in a sense, many of us would really like to break that standard model and to find out what else there is
Right, and
out
you
there.
say beautiful, rightly so, because we're going to say hello, bye-bye to Rebecca now, and we come back to CMS soon. We're going to
Okay.
move to point 8 of the LHC, where Guy Wilkinson, the spokesperson for LHCb, is ready to talk to us. Hello, Guy.
Oh, I hear you.
You can hear us well?
Yes, you hear me?
Okay. I hear you a bit not loud enough.
Your volume's a little bit low.
I'll get our people to work on that.
Yes, but it's understandable.
Okay.
So we were talking about beauty. What about beauty at LHCb?
Indeed. Our experiment is studying beauty quarks. Our goal is to make very, very precise measurements, and what we are trying to do is understand the difference in behavior between matter and antimatter. And a very good way to do this is to make precise measurements of the decays of beauty quarks.
So you're answering a very profound question, or at least you're hoping to answer a very profound question, which is why are we here? Why didn't we annihilate with antimatter in the early universe?
Exactly. In the early universe, matter and antimatter were produced together in equal amounts, and now we seem to have matter. We only seem to have matter, and this tells us that matter and antimatter behave in slightly different ways, and this is the purpose of our experiment, to learn more about this.
And the B quark is especially important for this?
The B quark is an ideal laboratory for these studies. In the B quark, there are many CP violating effects, that is, matter antimatter violating effects, which are very well predicted in our theory of particle physics, the standard model. So our purpose is to make very precise measurements to try and compare those measurements to the predictions of the standard model. The standard model cannot explain this imbalance between matter and antimatter at the level we have it in the universe, so we know there should be something else out there which is driving this, and therefore we hope to see discrepancies in our measurements.
Mm-hmm. Is there a big difference between what you can find in the standard model and what we actually measure?
enormous. The standard model is many orders of magnitude away from being able to explain the imbalance which does exist in the universe. So there should be a very clear signal. There are many ways to look at it, but certainly our measurement program is one of the most promising.
Guy, during the first run, LHCb performed wonderfully. You published a lot of papers. You made a lot of fantastic measurements. How is 13 TeV going to make a difference?
For us, the increase in energy is not the main benefit. The main benefit is the fact that we're going to collect a much larger data sample, and our detector is more ready and able to take advantage of this large data sample, and we will be able to increase the precision of our measurements. For LHCb, precision is all, and the bigger data sample that Run 2 will bring is very exciting from that point of view.
Thanks a lot, Guy.
And in fact, we are sharing this with our colleagues in the US, which basically have been waiting now. I think it's the middle of the night. There's a party ongoing at Fermilab,
Right.
so I would like to say hi to them. And okay, it's been a great moment when we started seeing the first tracks.
The LHC is back in business, we read on the LHC page 1.
Absolutely.
And CMS has started recording data. These data are going to be part of the Season 2 data lot?
Yes, that is Season 2 data lot, yes. CMS The Revenge. Yes.
CMS is back as well.
You can see we are preparing even things for a better celebration of things. So.
That's great.
We wait for you at the
missed out.
CCC then.
What
Yes.
will it take to open that, Tiziano? What
Well-
discovery will it take?
No, this is to celebrate the restart.
Okay.
And we have plenty in store for the discoveries.
But are you making a wish, Tiziano, for CMS? What's your best wish for the season of 13 TeV physics?
Oh, it's basically taking data steadily now and hopefully not to wait too long for being very excited about if nature is kind with us.
It's very, very good. And in fact, I'll tell my Atlas colleagues that we can come on over to CMS because they have champagne. Is that right?
Well, better hurry because it might be over soon.
I suspect we have our own bottle.
Okay.
So what's the plan for the rest of the day, Tiziano?
Well, for the rest of the day, I think we are planning to continue to take data, of course. This data is going to be already useful for some of the very, very first measurements, physics measurement at LHC. And I think, as I say, we are going to have a little celebration around here.
Fantastic. Well, congratulations on taking the data. And the race is on now. We're going to see who can get the best results before the next conference.
Yes.
That's our goal.
Okay.
Good luck, Tiziano, with this new hunting season for CMS. And we go now to LHCb, point 8.
Thank you. Ciao, Paola.
Bye. Guy Wilkinson, hi, welcome back. We made it. We have collision with stable beams at 13 TeV.
We did. It's remarkable. We're very pleased here.
Right. So, do you feel like a hunter entering a new terrain?
Oh, that's
A new unexplored season, or an astronaut
you,
landing on a new planet?
I tell you, I was here 4 or 5 years ago when we had the first LHC collisions. That was very exciting. But in some sense, today's even better. And that's because we now know what our experiment can do, how well our detector can perform. And so the potential of this new run is ever more exciting.
You have a
Very nice
refined
day.
weapon in your hands.
Yes, indeed.
So now that we've gone up to higher energy, this is the highest, well, almost the highest energy that we're ever going to achieve for the LHC, at least in the foreseeable future. The next step in for 3 years or so will be increasing the luminosity, creating more and more collisions, which will allow us to do even more physics, and as you mentioned before, to improve the precision of our measurements.
That's right. As you were asking me that question, this is a bottle of champagne was opened behind me. This is a very high-quality LHCb glass. Let me just
Cheers, cheers, LHCb.
toast the machine and everyone around. But But indeed, there's much to be done. What is important for LHCb is not so much the energy, but the increase in the data volume we will get. We want to make precise measurements. Precision is the name of our game, and this next run promises great advances in that terms.
Thank you, Guy. Let's move on to point 2, interaction point 2. Alice. Hello, Alice.
Hello, Paolo.
Who is speaking? Yves. Hi,
That's
Yves
Yves
Schutz.
speaking.
Yves, deputy spokesperson of the Alice collaboration. How is it feeling now at point 2?
Well, we almost already entered the routine business now.
Almost routine.
Yeah.
Celebrations are over already.
Celebration is
You're
over,
serious,
and
guys.
making ourselves ready to have to be ready to take the best data we can.
Well, we saw bottles of champagne opened over at CMS and at LHCb. Alice is in work mode. They have coffee there.
No alcohol in Alice. We want to keep clear mind.